If this works out, then Tony owes me a lot of beers.
This is the Convergent Science Network podcast. Leading researchers in the domain of neuroscience, brain theory, and technology are interviewed by Paul Verschure and Tony Prescott.
All right. Okay, it's Paul Verschure with Tony Prescott for the Convergent Science Network podcast, and today we're here with John Lisman, who was speaking at our summer school. And John, actually, this is a really special year for you because it's exactly 20 years ago that you published your paper with Idiart on theta-gamma cycle. And 20 years later, you're as excited about it as you were 20 years ago. So why is this such a big deal?
Well, ideas are nice, and it's much nicer when you know that they're true. And I think that's what motivates me. Actually, some people often will say, "Oh, that's such a great idea," and I think it's so beautiful, irrespective of whether it's true. And I understand that some people feel that way about their work, but I don't feel that way. I feel that it's only beautiful to me if it's true. So if it takes 20 years and it turns out to be true, I'm very happy.
Okay, but now just your happiness is not necessarily convincing others that it is true. I guess there's an empirical base for that, or not.
I don't know whether other people are convinced. I haven't polled them. Maybe you guys will tell me what you see as the holes. And I could talk about some of the holes myself, but in terms of representation, that is, in terms of what you can record, it seems to me completely convincing that, different information is held at different theta phases, and that it's not a continuous phase spectrum, that it's a discrete phase spectrum, and the discreteness is organized by gamma. So that seems to me experimentally clear. Now, what somebody could argue is that I don't even believe that this is a code until you show me that some downstream network or behavioral system is reading this, and that therefore if you put some altered information in a particular gamma slot, that the animal will behave differently. That would be, a reasonable next step. And so maybe one would really have to show that before one could claim victory. But I wouldn't go that far.
Okay.
Perhaps I think for listeners, we need to say what we mean a bit more.
Okay.
Because not everyone will have watched the talk. So let me try and briefly say what I think you mean. So we have these slower brain rhythms and these faster brain rhythms. Theta is between 5 and 15.
Okay.
Is that right, roughly?
Most people would. We don't really know exactly how to define these things.
Okay.
So, but that's not so bad. Let's take that.
And then the gamma range is roughly 3 times that, 4 times that?
Well, maybe from 30 to 100, let's say.
Yeah, okay. So really quite broad bands. And the proposal is that these are fundamentals to processing in different areas of the brain, and that they combine together so that the theta, that perhaps gamma is maybe, when you say that we're thinking in discrete ways, we're thinking in the gamma cycle peaks. And that the slower theta waves is modulating what can happen in the gamma spikes. Is that? Well,
I'm saying I think the fundamental idea is that some item, whatever you want to call it, it could be in the hippocampus, a place, is represented by the set of cells that fire in a gamma cycle. So we have a window there of, let's say, 5 milliseconds.
Right.
And now we come. And we can call that the first gamma cycle within a theta cycle. And that general concept is called nesting. That is, within a theta cycle, you have room for, maybe 6 or 7 gamma cycles, the faster rhythm. The faster oscillations are nested within a cycle of the slower oscillation. So now that I've said that one place would be represented by a spatial code in the first gamma cycle, we can say, well, is there evidence that different information is represented during the second gamma cycle? And the answer is, I think now, completely clear that the answer is yes. And so what you wind up having, is some sort of data formatting system such that within one theta cycle, which lasts, in the order of 150 milliseconds, you get to send a multi-part message. There's roughly seven parts to this message. And,
right. And possibly more, actually.
And conceivably more and conceivably less. So, we don't know the exact frequencies and how they might vary.
So you're proposing that the oscillations is providing a computational role, for instance, of chunking or packaging up information. Maybe in distant parts of the brain, you can form things in a package by where they fall. If they fall within the same theta cycle, they're in some sense part of the same package.
Well, if they fall in the same gamma cycle, they're part of the same package,
right.
I would say.
But then there's a hierarchy here,
right?
Sort of the theta forming,
right? And so then you can form a much bigger message, like all that would be contained within one theta cycle. So, what's a specific example of this? Yeah. This would be an example of the whole information of a transverse path. So, a transverse path would involve multiple locations between where you are and the goal. And now we have clear examples of a whole path being played out within a theta cycle.
Right.
But it's not a continuous process. It's discretized by gamma.
But that's the more recent work on hippocampus.
Yeah.
Right? So, and I think your original inspiration was not really linked to hippocampus. Your original inspiration was much more linked to ideas about working memory, about if you want the sequencing of memory, that memory has a certain capacity.
Working, yes, you're absolutely right. The original work was quite confusing to people, and that was fair, because the data that inspired this was data about theta and gamma observed in the field potential of the hippocampus. And then all of a sudden I started applying this to principles of working memory. Most people would not think of working memory as a hippocampal function. So there was kind of a sleight of hand in that original work. And, maybe it was lucky that it turned out not to be wrong.
But what was really the first empirical breakthrough that you think you found to support that idea?
Well, I think the first strong suggestion that different information was probably encoded in different gamma cycles was the John O'Keefe's discovery in the hippocampus of the theta phase code. So you say, well, why am I so excited about this recent work if O'Keefe had already shown that information, that the phase of firing of hippocampal cells within the theta cycle was so important? Well, what he didn't show was that the phase was discretized. And so that's what this recent Foster paper shows so beautifully. So now we know that you can't just have any old phase within theta. You can only have certain discrete phases within theta. So that, in a sense, really proves that you have to have something. And the Foster proved that the discreteness arises from gamma. Mm-hmm. So that really settles the issue. You have, on the order of 6 or 7 discrete chunks of information thrown at you.
Yeah, so in the Foster case, they were back in hippocampus.
Yeah.
And
okay.
You jumped forward then 20 years again, because this actually was published this year.
Right.
Right. And what you show there, so I have a rat, or the rat navigates through an environment, and what they've managed to do is really very precisely align the place cell response while I'm moving through this environment with the theta and the gamma cycle.
Right? Well, they weren't moving through the environment, but and this was the readout while the animal was still. But yeah, so I mean, in a sense, this very precise work was made possible by the fact that they had so many cells that they were able to decode position on a very fine time scale. And it's only because they could decode position on a very fine time scale that they could find out that actually the animal is thinking about position X and stuck in position X, and then 30 milliseconds later, suddenly it's thinking about position X plus 1. That's the amazing result, that it jumps. And so that's what discrete means. So it's not a continuous process. And so that's supporting this idea of a discrete phase code, of a theta-gamma code.
I mean, would you? So when you say discrete codes as opposed to continuous codes, that makes me think of a standard computer CPU, which obviously goes in clock cycles, which are determined by an oscillator. Right. I mean, are you thinking this is the brain's clock cycle?
Well, let's talk about the concept of a word in computer framework, right?
Right.
So what is exactly a word in computer? Well, I mean, it's a certain number of bits, and the bits are ordered, right? And well, automatically we have to say that, and they're ordered in time sometimes, right? So what are the analogies to the theta-gamma code? Well, one huge non-analogy is the information content. So this elementary unit in the brain, in the computer, is just 0 or 1.
Right.
And then but what is the information content within one gamma cycle? Well, it's almost infinite.
Well, I would say slightly different. If you think about a standard CPU, your clock cycle is how many instructions. You can do one instruction during a clock cycle, and then you can do millions of those within a second in a modern CPU. But the instruction set also changes, so that a modern CPU has a much bigger instruction set. So rather than just, say, adding 1 and 1 together, you can now do some fairly sophisticated numerical computations in an instruction. So that makes it faster. So, and if there is any analogy at all to what's happening in the brain, and I just want to push you on this to see if you think there is, then the clock cycle in the CPU is really saying that the way we're going to work is that we're going to do instructions one after another sequentially, and we're going to do them at this speed, and within that each time step we can just do one instruction, maybe apply one operator to something that's in memory, and in the brain, presumably what you would, if you're going to agree with that analogy, which you might not want to, you would want to say that in certain parts of the brain at certain times there appears to be something like a clock cycle, which is organizing computation into these sort of discrete steps.
Okay, well, let me talk about computation for a minute, and then you can tell me whether you see an analogy. So first of all, let's look at what happens within a theta cycle. Well, we have the first gamma cycle, and we have an ordered set. So already this buys you an interesting analogy. You have an ordered set over 60 or 70 or 80 milliseconds. You have this gamma cycle, the second, the third, and fourth. And so you get order out of that one. Without theta, you wouldn't have order. Now let's look at what happens in a gamma cycle. So first of all, as I was saying before, there's an enormous amount of information represented within a gamma cycle. This is the brain's way of doing things, is that I'm going to coordinate the firing of the million neurons in the dentate gyrus during one gamma cycle, and some percentage of them, let's say 1%, are going to be active, and that's going to represent the information that I'm representing in that gamma cycle. And so that's, how that's, probably a million bits of information, because you've got the spatial pattern, so many different spatial patterns that you can form given a million cells. So this is, just the opposite of a digital computer, which maybe in one step is 0 or 1. Here we have such a high dimensional thing. So the next question is, what kind of computation can you do within a gamma cycle? Is it just the cells that fire that represent X? No. In a paper that Paul and Cesar and I published, we showed that actually it's not unreasonable within that gamma cycle to do what could be called pattern completion or could be called an attractor operation. Why is that? Because let's say that the network receives input about a pattern, and that pattern is slightly corrupted and incomplete. So let's say 10,000 cells should fire, but of the 10,000 cells that should fire, in fact, only 5,000 are triggered. Well, it only takes 2 or 3 milliseconds for those cells, through their connections with other cells in the network and specific synaptic weights that connect these axons selectively to the cells that are part of that 10,000 pool. And as a result, 2 or 3 milliseconds later, bang, the cells that didn't fire will fire. The cells that are part of the pattern will fire, even though they weren't fired by the external input. So here's an example of pattern completion occurring within 2 or 3 milliseconds, i.e. within the 20 or 30 milliseconds that is allotted to each gamma cycle. So yes, you can do computation within a gamma cycle. So, okay, now we can step back from this and you can give me your opinion. How would you compare this to the way a computer works?
Well, I think the analogy might be with something like a graphical processor, which can do lots of parallel operations, for instance, on an image in one clock cycle. So the only thing that I'm really trying to say is does the brain have a clock cycle? Because as you say, some people will argue definitely not, and people will talk about, if they want to use a computer analogy, they will talk about event-based codes. So it's a continuous time system, and then you get spikes. And you do all the processing on those spikes, and it's actually, you're losing information when you say let's have time steps.
Well, let me tell you one more piece of information and get your opinion. So there's been a big debate about there are a group of people who are sort of anti-oscillations. And one of the things that they've pointed out, which is absolutely true, is that the periods of oscillations are not clock-like. The periods, if you look at, let's say, even during a theta cycle, and you look from one gamma cycle to the next and ask the question, how regular is the gamma period? And the answer is not very regular. And it's not only empirically true, but given current models about how gamma is generated, this sort of ping model that's just a negative feedback between the principal cells, inhibitory cells, then feeding back onto the principal cells, those models also do not predict that this is going to be a regular oscillation. So if you use the word clock, you'd have to say, oh my God, this is a terrible clock, because gamma period is highly fluctuating. So a downstream, one kind of operation that maybe in a computer you could do, but in the brain, according to the theta-gamma code, you can't do, is to say, given that I have seen a gamma, the output of cells during one gamma cycle, I can predict that exactly 25 milliseconds later, I'll get another big bang, right? That is not true. You cannot do that.
But maybe there's also another aspect to this that makes a computer metaphor maybe less helpful, because in a computer, it largely operates also on a segregation of memory and program, or memory and processing, right? These are strongly separated, and to keep the content and the operation synchronized, you have to clock the whole thing. Well, but if you look at this hippocampal process, it's not so obvious that, let's say, the memory and the process are actually differentiated. And maybe the problem you will have much more if you are a hippocampus or a brain is to impose some sort of order on these continuous streams of events that you're bombarded with. So maybe more this event-based interpretation that also Tony mentioned earlier. So another way maybe to think about the theta-gamma cycle is that first you try to get to some sort of a temporal segmentation of these continuous input streams through theta, but you rely then very much on these local competitive processes that give rise to gamma, so the excitator-inhibitor interactions that are fairly local, to then fill in within those short segments that theta gives you what the most, let's say, dominant features are in that local process. Because the other thing we shouldn't forget about, it's not that theta-gamma as we now see it in the hippocampus is all there is to it, because actually gamma is something that is playing out in lots of local volumes in a completely desynchronized fashion, because it is just the range of an interneuron, you could say, that dictates what the sizes of a population of excitatory cells that play a role in generating gamma. So if you go, let's say, a few millimeters further down, you have a very different kind of, let's say, gamma encoding taking place. It has nothing to do anymore with the first one, but still they're all being then, if you want, aligned in time through the slow cycle of theta. And then if you talk about the clock, maybe the clock is much more at the level of the theta cycle than gamma. Gamma is much more asynchronous and local, but the real clock, if you want to talk about the clock, is then the system that dominates the theta cycle. So how regular is theta compared to gamma?
I'm not really sure, but my guess would be that theta is maybe even more irregular. In fact, we don't really even know how to distinguish theta in the cortex from alpha, and this is all very confusing right now. In other words, where do these names come from? And the answer is they came originally from the EEG field, and they had zero intellectual basis. That is, it was just arbitrary. They said, okay, let's just define this range by one Greek letter and this range by another Greek letter. And so, we've just all been very confused by, whether to make a big deal out of the difference between 8 hertz in the hippocampus, 7 hertz in the hippocampus. And maybe that's the same kind of process as 10 hertz in cortex. I mean, who's to say?
But but we have maybe a handle on that, right? Because that we know the origins of these oscillations, right? So gamma is seen to arise out of a local circuit where excitation inhibition interacts, right? I think there's consensus on that, whether it's cortex or hippocampus.
Fair enough.
This is seen as a source of gamma. Okay, that means then that rhythmicity and regularity will depend on the local properties of that circuit.
Right.
Theta in hippocampus is seen as arising from the septum.
Okay.
Right? It's really as a driver of this slow oscillatory response. For the cortex, might be the thalamus that dictates, or it will be the thalamus that dictates the slow rhythm. Right. So if you now look at the sources of theta and gamma.
Well, as you said, I think you were on the right track when you said, maybe what's really important in terms of interactions between brain regions is the slow oscillation. And that does maybe have to be synchronized between areas that communicate. Maybe the gamma is not so important. It's all local.
But I think the notion of a clock, although in a computer it's going to be a metronome, it doesn't have to be, because the key word for me that John said was discrete. So you have a cycle and it may be varying in its timing, but as long as the different parts of the system that need to understand each other are on the same point in the cycle, then the order that you're imposing by saying I'm only going to treat things within a gamma cycle as being together, and I'm going to take these bunch of events that happen with the gamma cycle and treat them as one event in some way and process that. So that seems to me the strong claim you're making, that the brain buys some usefulness from this binding of everything together into discrete chunks, and that this is maybe makes more sense than just having all these continuous processes. Because if I'm a bit of the brain over here, listening to this bit of the brain over here, I'll have to listen continuously and integrate everything that's happening in order to get to know what's going on. But you're saying I get a series of snapshots with the gamma cycle, or maybe with the theta cycle, and I can just pay attention to what's in that snapshot.
Let's
don't like that metaphor either.
No, I like it, but I want to propose that we use another word.
Okay.
Instead of snapshot, movie.
Right.
And why do I like that? Because let's say in the experiments that we've been discussing today in various forms, the Johnson-Reddish experiment, where the animal, in a sense, gets a view of what happened if it goes down one path of the maze. So what do I mean by view? Well, what the data show is that each point along the path is represented, and that is a movie. That's not a snapshot.
It's a sequence of snapshots.
It's a sequence of snapshots, which is a movie.
Mm-hmm.
And I mean, that's really impressive in terms of decision making, because you're getting that movie, within less than 100 milliseconds, and that's very valuable information. And I was discussing before with Tony, one thing I really, really like about now imagining how the basal ganglia evaluates this movie. The movie can be rich. The movie can say, last time I turned left, and, the first thing I came to was, some breadcrumbs, and that was okay. And then I went on, and I smelled some cat urine, and I thought for sure I was going to get eaten. But, finally I got to, to the reward side, and there was some really yummy milk. Mm-hmm. Okay. I mean, so you have costs and benefits about the left choice. Well, all of that information is passed within less than 100 milliseconds to the basal ganglia. And I think that, current models of the basal ganglia would allow you to actually integrate, to evaluate each of those steps within, let's say, one gamma cycle, get the value or the costs and the benefits, and wind up at the end with some sort of integrated number which told you the sum of the costs and the benefits. Mm-hmm. And that's wonderful. I mean, and we know that that's the way we want to run a railroad, is not just to look at what's at the end of the path, mm-hmm. but to know that, what we're going to risk if we take that path along the way.
Yeah, so the point there is that another element, I think, that you have not emphasized yet, even though you've been dealing with it. What's maybe more important is that also, if you are a brain, which we all are in some way, you have to progressively throw away more information and distill things down to what really matters. And also the way you think about the gamma cycle, it's also a progressive deletion of noise, if you want, because also what you're saying in the gamma cycle, I can generate 7 plus or minus responses within a theta cycle, but these are all the result of a local winner take all. So what I'm going to report in the theta cycle is the stuff that really stands out for me among possibly hundreds of possible responses. So if I'm in this maze, like we take the Johnson and Reddish experiment, I'm at the T crossing in the maze. I imagine I'm going to the left, so now I have a sweep through my hippocampal representation, right? Within this gamma cycle, I have 100 milliseconds. And now I sort of, what pops out are actually the most relevant spots I might visit there. It's not all possible spots. So it's also this incremental selection that might be an important role here, and not only how the information is processed further downstream.
Okay, well, now we get into a really complicated area of episodic memory. So, I mean, strictly speaking, what you would recall, if we really think in terms of episodic memory, is one of the times that I went down that path. That's what, if you take the point of view that the hippocampus is really the episodic store, and that what Johnson and Reddish is seeing is a recall of one previous traversal, not the statistical properties of all previous traversals of that path, but one of them. Then we get into this whole area of, is this the way you want a railroad? Do you want to use your hippocampus to remember individual events? And then if so, which exact ones do you recall? Or do you want your hippocampus to be statistical? I take the point of view that, the great thing about the hippocampus is that it recalls an individual, at least it hopes to recall an individual trial. And that has pluses and minuses. It says, that time on July 4th when I went down this path and, I thought there was going to be a cat, but, there was actually a buzzing going on and there wasn't a cat. So this time, if there's not a buzzing, if there's a buzzing go, I'll take the risk because maybe there's not a correlation. I mean, all that detail could be important in making your next choice.
Yeah,
but that's not statistical. And I mean, I love the idea that people have shown that actually, if you use your episodic memory, you will often make worse choices. So my favorite example, and I've heard that these experiments are a little controversial. They did the following. They showed people two houses, and they went through each house. So this was done probably on a computer, and they said, oh, here's the kitchen. It's a wonderful modernized kitchen, but here's the bath. It's not really ever been modernized. And here's the bedroom. It's really large, but here's the living room. It has a great view. And the costs and benefits of the two houses were very different. And in fact, they had arranged it so that they thought that most people would pick house one as the better house. Okay, now they had two groups. After showing them these two houses, one group was told, please do this arithmetic problem. And the other group was told, think about this house. Then they asked them which house is better. And, one can argue about whether it's possible to decide objectively that one house is better. But anyway, the people who did not think about it were better. Now, why would this be? Well, there's actually a very interesting and I think useful explanation. Probably what happens when you're using your thinking is that you get stuck in silly examples. You say, that kitchen reminded me of my least favorite aunt. And, she, damn it, I went to her house and she gave me this porridge that was just disgusting. And you're spending all your time thinking about this aunt, so you actually aren't thinking about all the other rooms, right? And so it turns out that your basal ganglia, which is sort of more statistical, actually winds up doing a good job because even, your episodic memory isn't sampling very well. Anyway.
But I don't buy that. I think there's a problem here. I'm sorry to bring the bad news, but earlier you said, and you referred to a paper we published together, that memory is based on attractor dynamics.
Right.
And by virtue of that, you can do pattern completion, for instance. Right. But an attractor dynamic has, by necessity, statistical properties because it will pull input states towards some average state.
Mm-hmm.
So in that sense, to then declare that attractor state as a factual, accurate representation of a single sampling, I think would be a really long shot. How are you going to defend your attractor from drifting? And that's actually one of the things we showed, right? We explained also in that paper that the drift that people saw in the kind of CA3 memory when you change the environment. So now we are actually visiting the houses, but we're slowly changing them. That there is a drift in that memory. And that drift is then also an expression of a statistical property that you are averaging over experience, right? So isn't the idea of an attractor dynamic based memory actually forcing you to also commit to a more statistical interpretation of episodic memory?
Well, let me try to see if I can argue the other way. I mean, why is the attractor relevant when you think about the kitchen in that house you were shown, and it was because it was really very similar to your aunt's kitchen. So there's the attractor. So we've utilized the attractor. But if it was just generalized kitchen, right, you're saying it's really a kitchen attractor, it's not my aunt's kitchen attractor, then it would bring up associations with all kitchens, which might be very positive on average. But in fact, what happened was that it was not generalizable. That kitchen just got you stuck in your aunt's kitchen.
I think we're possibly looking at a false dichotomy here, because what you want for your episodic memory is to do pattern completion. So you want to be able to fill out what's happening now based on things which have happened in the past, which are relevant, which may help you interpret that situation. So you're in that kitchen, you're reminded of your aunt's kitchen, and that might also make you think then, well, maybe this kitchen has got some of the properties of that other kitchen I was in, and that might be useful for understanding that scene. So the pattern completion is going to partly depend on many possible past events which are relevant to interpreting this one. And then the other thing you want to do is pattern separation. So you want to, and you want to be able to say, but this isn't my aunt's kitchen. So although I remember it as being similar, it's not the same thing. So your episodic memory has to be able to distinguish this kitchen from previous ones, which is what you're saying, is that we needed to do both these things. And the fact that I think it can do both, but it doesn't do either of them perfectly, is the thing we want to try and explain about episodic memory.
That sounds like a very nice compromise. I'll go for that.
Good. At least John will not demolish the studio now. That's great. But so now we have an idea about this episodic memory in the hippocampus, and we want to use that as a way to understand coding in the brain, right? And what we see there is that this episodic memory that's playing out on the slow oscillation of theta in the gamma cycle is telling us, let's say, what's the most relevant, what are the most relevant aspects of the processing going on within this piece of volume of the hippocampus. But now if you go back to the data of Foster that you talked about earlier, where they've with very great temporal precision unpacked the response in the gamma cycle, in some sense it showed again a further complexification, because it's not that on every single gamma cycle there's just a single spike. You have multiple spikes riding within that gamma cycle. So can you imagine that the nesting would go further than only theta, gamma, but that also go, let's say, low and high gamma?
Well, first of all, we don't really understand anything about the differentiations between low and high gamma. And there's one really, accepted place where you see these simultaneously, or at least overlapping, and that's in the high gamma that comes into CA1 from the cortex, and the low gamma that comes into CA1 from CA3. And it really just unclear to me what this all means. I don't think anybody knows. One surprising thing is you might say, let's look at the output and see who the output is listening to. And the answer is neither. The output just has its own gamma, not tied to either of them. So, I mean, one very simple way of looking at it, which I favor, is that, inputs are coming in and the cell is integrating them on its own time constant and deciding how to output the information on its own. That's not tremendously satisfactory, but that seems to be the best description that I can come up with of what has actually been found.
But that seems reasonable, right? Because let's say I'm in CA3, I'm packing up information in my gamma cycle based on a local competitive process. Now, what I'm telling CA1 about, the next station upstream or downstream from me.
That would be the subiculum. The downstream from CA1 is the subiculum. I was just talking about
at CA3, right?
I was talking about CA1.
Okay, right.
So downstream of CA1.
No, but I want to start at CA3 because I want to say, basically CA3 makes a pre-selection and said, okay, these are the few items that I care about. So it has filtered out a lot of noise. Now CA1 will do something similar because it now gets this whole barrage of inputs from CA3 still and has to make a selection. So again, it selects within its own gamma cycle using the same competitive process to tell the subiculum what it really cares about.
Yeah.
So it's really also a hierarchy then of competitive processes. So this is how you think about it.
I don't know. I think this is just going to, I personally would think that a lot of effort should now be put into understanding CA1 because it's just so fascinating and what's happening, and we have so much data, and some principle is going to emerge, but I honestly have no idea what it is, but I actually think I'd like to spend some time seeing if I can figure it out.
So then we earlier in the week, we also had quite some information presented to us by Edward Moser on the grid cells. And the grid cell story actually for the last 10 years looked so clean and nice because here we had these cells in the entorhinal cortex, input to the hippocampus, have a very nice grid-like response to space driven by velocity. And this might then be a great substrate for place cells in the hippocampus to learn about space, right? Now that story has become more complicated because it looks like place cells can develop place fields in the hippocampus even if you have no grid cells available to you. So the place cells are way more promiscuous in that sense than initially anticipated. So that might give us some space to also speculate about what these grid cells really are for if they're not really the only source of spatial information. So it was up to you. How else would you abuse the grid cells?
Well, we very much favor a new view of grid cells. And the question is, what functions are there out there that you have to account for, and which ones do you want to assign to grid cells? So classically, what people have said is, well, you have sensory information about the outside world. Here I am. People have said path integration. I integrate velocity. So if I knew where I was, I integrate my velocity. I know where I am now. And then this interesting phenomenon, which we've talked about earlier on the basis of Johnson and Reddish, which is I'm not moving, but my mind is going to move down one of the paths. And we call that mind travel. So in the end, we have these three functions. How are we going to build a system that does all three? That's what we've got to do. And by my way of thinking, the grid cells are really well suited for doing this mind travel. So they move you in an imaginary way through space. They can integrate, but what they integrate is not your actual velocity, but some artificial velocity, which part of the brain generates, saying, I'm curious about what happens if I move down in this direction with this velocity. And then the grid cell system can give you the answer. It's a coordinate system that says, well, given this velocity in this direction, this is where you will be. And it gives you that path. The beauty then is that it can force that movement through space on the hippocampus. What can the hippocampus contribute to that? It can contribute associations that happened with those places. So if there was reward or a cat associated with some place that you mind travel to, that's incredibly valuable information. So I don't think that the grid cells know about cats or food, but they do know about the coordinate systems of space. So you move through space and you tell the hippocampus, here's how we're moving through space. And then the hippocampus says, given that you've made me move through space, this is what I found associated with that. So then we would say, well, great. If that's what grid cells are good for, don't we also have to do path integration? Well, we can make some suggestions that it might occur earlier in the structure, and there's some interesting candidates about where path integration might occur. So that's the integration of real velocity.
So I have a bit of a worry about this story because Edward Moser presented this beautiful data set, and his interpretation, or my interpretation of his interpretation, is that we have these modules at different levels of granularity, which are giving us this wonderful metric map of space, so that when you come into this room, that metric is laid out over the space so that every point in space now has a unique code assigned to it across these different modules of grid cells. And it's anchored possibly at the door or some other point. All the grid cells always seems to have an anchor at the place that is introduced. Or now I've got this metric map of space. I can navigate in it. But your suggestion seems to be that you're going to take my map of space and you're now going to start moving it around. So I'm no longer on firm ground, knowing what my coordinate frame is, because my coordinate frame is shifting. You're moving it around. Or have I misinterpreted what you're saying?
Maybe misinterpreted, because when you described Edward Moser's proposal, I found myself nodding. Not nodding to sleep, but nodding in agreement. And so,
okay.
So the answer is, I think that I would agree with everything you said. It's a coordinate system which allows navigation. The question is, what do you use that coordinate system for? And it's the nice thing about it, it's a pre-wired coordinate system, so you can use it in any environment. You just have to attach it.
Yeah.
To a given environment. And now you have the means for saying, well, if I look this way, where will I wind up? Or if I go this way, where will I wind up? Which is what I'm saying.
Right.
So I don't think we're at odds. The only no, I guess I don't see them as contradictory.
Okay, I guess you're putting the ability to move within the map in the grid cells, which are themselves the coordinate frame map. And I worry a little bit whether you can do that, whether the grid cells just have to form the coordinate frame and then some other system can represent movement within it.
Okay. So I think you did say one thing that really I'm forced to come back to and admit that's a problem and suggest a solution. And that is, if we use the grid cell system for for these imaginary movements, then how do you reset it at the end of a theta cycle so you're back to current position? Because we've sort of mucked with this.
Yeah.
Right? And, my proposal is that we do have another integrator, which is integrating true velocity, and which is, in a sense, doing what everybody thought the grid cell system would do. So, you could say, well, I've made life more complicated now because now I have a whole other system which is keeping track of actual position. Another grid-like system that's keeping track of actual position. And that can, since it knows where I am, can reset the grid cell system to current position after I muck with it and make it do this imaginary movement. You were absolutely right. You have to, after you do the imaginary movement, you have to move back to current position. So somebody must know current position.
Yeah.
But, I mean, it's not, this complexity is demanded by the fact that we see these imagined movements through space. So somebody's got to be doing this. So if you take another model, they also have to solve these dual requirements.
Yes.
But I think both of you are much too pessimistic about this because on the one hand, why would I even need a parallel system for that? Because I just need to replace my velocity vector, right? Either the velocity vector comes from my vestibular system or optic flow, whatever, and it tells about physical movement in space. And with that, I'm driving my grid cells to get a response. This signal is arriving in the entorhinal cortex over the thalamus, so I have a number of stages in this pathway where I can basically hijack the signal. I can pump in anything else I want. I drive my grid cells around again. Now you have and the point is, so far the data, at least on rats, has shown that if they mind travel, like in the sweeps we've seen Johnson and Radish, or Pfeiffer and Foster, the animal's standing still. The animal's not moving, right? I'm not aware of any data where the animal is actually doing this kind of mind travel as it is moving. So that means as I now start to move, I take over this whole channel again to pipe a velocity signal into my grid cells.
Let me stop you, Paul, because I'm afraid I have to tell you that the phase precession, the interpretation of the phase precession that I think everybody would accept at this point is that while the animal is moving, it is looking ahead. It is,
but not in this extreme way, as is shown in, let's say, the Johnson and Radish sweeps or the Pfeiffer and Foster paper.
But it nevertheless is. And I mean, the interesting thing is now when we come to experiments, right? So why do I think I'm on the right track? Because this looking ahead that occurs while the animal is moving, which is reflected in this phenomenon called phase precession, that does disappear when you get rid of the grid cells or when you get rid of the medial entorhinal cortex. So there is some experimental basis for this, but the place cells survive. So we're beginning to get experimental support for this dissociation. In fact, it's this sort of dissociation that sort of was the demise of the previous theories. So, I mean, we're starting to get a lot of data, which now begins to differentiate between different models. And this model that we're putting together now, I think is at least consistent with all the existing data. It may fall apart when new data comes, but this is where we're at.
So, I mean, I think I'm more happy with your model if I'm understanding it correctly, which we have this metric map which is anchored to the room. And all you're saying is that the grid cell, activity in the grid cell can represent the fact I'm moving around in an imaginary way in the room, and that different patterns of grid cells are firing to represent those different points I'm visiting. That will then feed through to CA1 to represent the non-spatial features of those locations in space, what it would look like if I was standing there and looking around. And yeah, I'm fine with that because my metric map is anchored. When I open my eyes and look, then I'll be my grid cell map. I'll be back at the point in my grid cell map where I really should be. So I'm not sure there is a problem that you're describing. I thought you were co-opting the grid cells to do something other than have a stable metric map of space.
No, I was not.
Yeah. It's only the velocity vector that's changing, actually.
Right. And McNaughton has tried to generate models in which all you do is you have one sort of grid cell system which is responding both to real velocity and to artificial velocity. So the idea is that I know where I am because I've integrated real velocity, but now I'm going to add an additional velocity and move imaginary through space. And now what he does is has a speculation about how you can subtract out that artificial velocity, in a sense, make it a negative, and so that puts you back to where you are. So here you could deal with two kinds of velocity in the same network. And my only difficulty with that is that it's computationally difficult to have two velocity terms and then subtract out the effect of only one of them. It's not impossible, but it's not elegant. And therefore I favor the view that you just keep it elegant and have one guy who's dealing with true velocity and another guy who's dealing with the artificial velocity, but who can be reset after all is said and done by the guy who's keeping track of real velocity. It seems more elegant to me.
But now, but also what you would be saying is that in my look ahead with this mind travel, I have a finite capacity to look ahead, right? I can only do that for how many theta cycles? It's one full theta cycle, but with the 7 odd gamma responses I have within that.
Yes.
So if you want to now look ahead, let's say if you are in an environment that you know very well, like Woods Hole, you might be able to look ahead basically to any kind of street, any possible trajectory, with much higher precision and much further depth in space than you can do in a novel city like here Barcelona. So how then can I change the spatial scale and my resolution on which I can look ahead if everything has to happen within a single theta cycle?
Well, we strongly suspect, based on some evidence, that the whole system is just replicated along the long axis of the hippocampus at larger and larger scales. So the dorsal part of the hippocampus, which is the one that's almost exclusively studied these days, keeps track of very small distances. I mean, we're talking about distances, of a foot or so. In contrast, the ventral hippocampus, when you look at the size of the place fields, when you look at the phase precession, is looking over meters. I'm changing units here, but that's okay. I'm in Europe.
Yeah, don't worry about it.
Confusion is expected. So, and we were talking with David Radish the other day about, well, why do we know so little about the ventral hippocampus? It's because it's so hard to study. It's hard to get an electrode in there. And, it's so easy to generate lots and lots of data because you can get in the dorsal hippocampus, you not only get an electrode in there easily, but you get a zillion electrodes in there easily. So you get really rich data sets, and it just isn't true. But, at this point, some data is available about the ventral hippocampus, and then I think we'll have, more answers to your question at that point. But the available data does show that the scale changes.
So then do you see this as a unique feature of hippocampus and temporal cortex, this ability for mind travel? It's unique, or can cortex also mind travel?
That's a very interesting question. Maybe this is a good point to end. I have no idea about that.
No, we're not going to end here, John. Okay, let's see what the future brings us. But now, so this is amazing, right? This is a great moment. You're gonna all buy us beers later on. 20 years of theta-gamma coding,
right?
And we still could not talk it out of your head, even not in this podcast interview. I think you're still going strong on that.
Thank you.
Now, having fought this battle now for so long, and still standing and smiling, what is John's law that we should adhere to study and understand the brain?
To study the rest of the brain.
Everything. What's John's law? What assures progress in understanding the brain?
Wow.
I'm going to write it on the wall here. John's law.
Right, John's law, right.
You just have to define it.
Yeah. That it's not as complicated as you think. That is to say that, if we think it through carefully, we'll see organization principles fall in. So I'm definitely think that people have underestimated how quickly we will come to understand the brain. And I think that understanding the brain is a lot like solving, other kinds of puzzles. And when you look at the process, let's say, of a jigsaw puzzle, at first you don't see the patterns, you don't know how to recognize certain, uniformities of colors and patterns. And you also don't have many constraints. But everything changes, when you get near the end. You understand the rules, you have constraints from other, pieces of the puzzle, And everything just goes very fast as you get near the end. And I think we are getting to that point.
Mm-hmm. Okay, so don't get confused by complexification.
Right.
So now the other thing is, John, as you know, Tony likes traveling and he likes hamburgers and Captain Kidd. So 5 years from now, he wants you to take him to Captain Kidd in Woods Hole. And then he will confront you with a prediction you're going to make today that you will have proven right or wrong by then. So what's the most important prediction you would like to commit yourself to that needs to be verified by that time?
Oh, well, that's easy because, even older than the theta-gamma idea is the molecular basis of memory, CAM kinase, that now we have refined that model to say that it's the complex of CAMK2 with the NMDA channel at the synapse that is the actual molecular memory. And in my own lab, we've done the critical test to see whether we could erase LTP by attacking the CAMK2 NMDA complex, and we could. So that was great. And so now we have set up upon the next phase of our work, which is to erase a behavioral memory. So we have everything set up. We have a nice learning task of spatial memory. We have a virus which contains a dominant negative form of CAMK2. And so what we're doing is to put the virus into CA1 and see if we can make the animal forget. And we've even arranged this to be a spectacular form of virus which does just what we want. It turns out to be an HSV virus. And what's so spectacular about it is that it only expresses for 2 days. And so what we can do is teach the animal something, inject the virus, let it do its thing, but then it's gone. Now, if the memory is gone, when we measure 10 days later, all those negative, nasty reviewers, they can't say, well, the virus is just mucking things up, because then we can say, no, the virus is gone. And the only reason that, the memory is not there anymore is because we've erased it. Mm-hmm. That's what we want to say. We want to say we were able to erase it.
Cool.
And so we think we have so if this works out, then Tony owes me a lot of beers.
Great. John Lisman, thank you for this conversation.
Okay.
Thank you.
Thank you.
The CSN podcast was produced by the Convergent Science Network of Biomimetics and Biohybrid Systems, a project funded by the European 7th Research Framework Programme. For more interviews, recorded lectures, or upcoming conferences in the field of biomimetics and biohybrid systems, go to csnnetwork.eu. And thank you for listening.
That's great, on the anniversary of your paper.
So let's see. How old do I have to get? If it's before I prove the CAMK2 hypothesis, if it has to be in years of 5.
Exactly.
I'm not going to live that long, I don't think.
But that sounds like a fantastic experiment. Thank you for generating a prediction on a topic that we hadn't discussed at all. Well, that was very helpful, John.
It was fun. Yeah, it was very good.